There are several factors affecting cell conversion efficiency. The materials of the cell, the wavelength of light entering and hitting the silicon, band gap, which I'll explain in a minute, temperature, obviously as the temperature goes high, efficiency goes low, reflection within the cell, light beam that goes into the cell, penetrate the cell, is reflected back, and we lose that energy. Those number of photons which are being reflected back cannot excite electrons and cannot create a current, they just reflected back. Electrical resistance of the conductors. They have natural in-house resistance, resisting current from flowing. Material. Much of the energy from sunlight reaching a PV cell is lost before it can be converted into electricity. But certain characteristics of the solar cell materials also limit a cell efficiency to convert the sunlight it receives. So the material itself should be as pure as possible to allow electrons to move freely from the N-type to the P-type side of the semiconductor through the junction. So materials is basically parameter number one, loss number one. On the top, we see the conductors. On the bottom, we see the conductors. We can see it very, very good in the left picture. There are multiple conductors on each of the side, and they collect the electrons. If the material is pure, more electrons will flow. More electrons will go up to the upper set of conductors, and more holes will go down to the lower, bettering the battery. The battery will have higher voltage output. Wavelength of light. The primary reason PV cells are not 100% efficient is because they cannot respond to the entire spectrum of sunlight. We can see where the spectrum is on the left-hand side. And that's very, very narrow area within the total light spectrum. If we would increase it, there will be more area, more range, better range, wider range of wavelength, where we can actually make use of effectively the solar energy coming into the cell. When light strikes the surface of the solar cell, some photons are reflected and they do not enter the cell. Other photons pass through the material. Of these photons, some are absorbed by only having enough energy to generate heat, and some of them have enough energy to separate the electrons from their atomic bonds to produce charge carriers, negative electrons and positive holes. So it's a portion of electrons of photons that can actually create electrical energy. Bandgap. It's defined as the minimum amount of energy needed to free an electron from its bond, and this energy differs among semiconductor material. Photons with energy less than the material's bandgap are not absorbed, which waste about 25% of incoming energy. Not every single photon has an identical energy to the other one. Some have more energy. The ones which are not will not create electricity at the end of the road. The energy contents of the photons above the bandgap is wasted surplus, re-emitted as heat or light, and accounts for an additional loss of about 30%. Thus, the insufficient interactions of sunlight with cell material waste is about 55% of the original energy, 25 plus 30. So only very few photons, less than half, are really having enough energy to create electrical energy. Natural resistance of the material itself. The natural resistance to electron flow in a cell decreases the cell efficiency. These losses predominantly occur in three phases: in the bulk of the primary solar material, in the thin top layer typical of many devices, as the interface between the cell and the electrical contacts leading to an external circuit. These are natural resistors parameters that associate with the material itself. A conductor has a resistance. Temperature. Very, very important efficiency loss factor. PV cells work best at low temperatures. All cell materials lose efficiency as the operating temperature rises. Much of the light energy shining on the cell, 80 to 85%, becomes heat, not electricity. So it is good to either match the cell material to the operational temperature or continually cool the cell. I have to make sure that the temperature of the cell will be ambient, as close as possible to ambient, as close as possible to 20 degrees C, 25 degrees C. This is where I want the cell temperature to stay. In a minute we'll see some examples. What is the effect of temperature on the loss of efficiency? Let's look at some effect on IV graph related to temperature. IV graph is the basic graph of photovoltaic system. It's basically a multiplication of the I current with V voltage to come out with power. The basic graph is the one on the top. The vertical axis is current. The horizontal axis is voltage. And we have an MPP point, maximum power point, MPP, which is the Imax and the Vmax. The multiplication of these two values will give me the maximum power. It's the MPP. And my purpose is to push to the right this MPP point, to make the multiplication bigger. In other words, to increase the current and to increase the voltage, so the multiplication will be bigger, therefore the power will be higher. Let's look at the lower three graphs. On the left, photovoltaic array power output versus irradiance. As the temperature increases, the output power is being decreased, and we can see it. The one on the center, photovoltaic array temperature characteristics, PV voltage versus PV current. As the temperature rises, it pushes the graph to the left. So the multiplication of the I value and the V value will give us lower power output. The one on the right, photovoltaic array DC efficiency versus irradiance. As the temperature increases, it reduces the DC efficiency on the same irradiance. So from these three lower graphs, we can understand, we can appreciate the importance of keeping the temperature at its lowest possible. Now, a very important parameter when we look at the cell and when we look at the panel is what it called NOCT, Nominal Operating Cell Temperature. The standard of verifying whether a cell is good or bad is looking at the standard, testing that cell according to some standards. And the standard is 800 watts per square meter, irradiance, ambient temperature of 25 C, wind speed of 1 meter per second, and a model tilt angle of 45 degrees to the sun. These are the standard environmental conditions helping us to test a cell. The difference in cell temperature and ambient temperature is dependent on sunlight intensity, the watts per square meter. Let's take an example. If a particular panel has a NOCT of 40 degrees C and a maximum power temperature coefficient of minus 0.5 degrees per degree centigrade, the power losses on temperature can be estimated as, this is the formula, 0.5% times the difference between the 25 degrees, which are the reference, and the actual temperature. The difference is 15. 15 times 0.5 is 7.5% loss because of the temperature. And this is because the NOCT was 40 degrees C and half percent loss for each additional degree above 25. That's a very important parameter. 7.5% is a major loss. So when we select a panel and when we look at a technical specification of a panel or a cell, let's look at the NOCT. We want to look at smaller as possible number. 0.5% per degree C above 25 is a very big number. 0.4% is a better number. 0.3 is even better. So we have to be careful because the loss is significant. And the effect of the temperature, the output of a solar cell, and therefore a solar panel, is affected by its temperature. As a result, the power output will be reduced by between 0.25% in a thin-film technology and 0.5% most crystalline cells, the polycrystalline and the monocrystalline. Now, this is for each degree of degree centigrade of temperature above the ambient 25 C. Panel temperature in the summer in warm climates can easily reach 50 degrees C surface temperature, which will result in 12% reduction in output compared to rated output at 25 C. That's a tremendous loss. So we better look at the technology of the panels and make the right selection according to the environmental parameters of the location of the PV system where we want to install. In the desert, for example, where surface temperature can go up to 70 degrees, we touch the surface, we touch the glass of the panel, and it gets very hot. So the loss will be about 15%, which means for the same level of output power, we will need 50% more area, 50% more panels, 15% more money to invest, just because of the NOCT. So that's a very important parameter. This reduction in efficiency may be incorporated to you if you have a high electricity demand in the summer. Let's appreciate the problem. If I have a high demand of electricity in the summer because of air conditioning systems, etc., and this is a time where I have the maximum losses because of the high temperature. So there should be a balance between the consumption of energy in the summer versus the NOCT, which is the basic parameter in terms of the efficiency of the cell. So we should be very careful when we calculate a system because it affects the amount of investment or the loss of money or the loss of efficiency, same thing. Another parameter associated with loss of energy is reflection. It's an internal reflection within the cell itself. It's light beam that gets into the cell is being reflected back out. The photons that are being reflected back out do not excite electrons, do not produce current. They are reflected back and out. A cell efficiency can be increased by minimizing amount of light reflected away from the cell surface. For example, untreated silicon reflects more than 30% of the incident light. 30% of the incident light is a lot. It means that if 100% goes in, only 70% have the potential of being converted to electricity. That's why various anti-reflection technologies help us to optimize light absorption. Most commonly, a special coating is applied to the top layer of a cell. A single anti-reflective layer will effectively reduce reflection only at one single wavelength. Better results over a wider range of wavelengths are possible with multiple anti-reflected layers, but that means I have to have a cell of N, P, N, P, N, P with several layers, and each of them will have an anti-reflective layer in between. But I'll get higher energy at the end. Another way to reduce reflection is to texture the top surface of the cell, which causes reflected light to strike a second surface before it can escape, thus increasing the probability of absorption. Let's look at the picture. We see light being coming in, it's being reflected to the side, some of which penetrates the cell itself. If the front surface is textured into pyramid shape for anti-reflection, all incident light is bent so that it strikes the polished, but otherwise untreated, back surface of the cell at an angle. This texturing causes light to be reflected back and forth within the cell until it is completely absorbed. It's a very, very interesting technique, now mostly used in major panel manufacturers. Now, the electrical resistance of the cell itself in terms of the conductors. Larger electrical contacts can minimize electrical resistance, but covering a cell with large opaque metallic contacts would block too much incident light. So the wider electrical conductor, meaning less resistance, meaning the electricity will flow much faster, much easier, with less losses. However, there's a drawback to this. On one side, I would like to widen the conductor, but if we widen the width of the conductor, we cover too much silicon area of the cell itself. So instead of 100% of silicon area in the cell, I'll have 97%, 96%, 95%. So I'm losing silicon area. I'm making the life of the electron to flow easier, but the electrons that will be collected by the conductors from the silicon, the number of electrons will be lower because there is a less area. Therefore, a trade-off must be made between loss due to resistance and loss due to shading effects. Conductor is basically create a shading effect. It covers the silicon. It sits on it. Typically, top surface contacts are designed as grids with many thin conductive fingers spread over the cell surface. Many thin, very, very thin. Just to make sure that I'll get most area of silicon on the surface exposed to the sun. To continue with electrical resistance, generally the back surface contacts of the cell is simpler, often being just a layer of metal. That's in the back. Other designs for electrical contacts include placing everything on the cell's back surface, or as in some thin films, depositing a thin layer of transparent conducting oxide across the entire cell. The front conductors create shadows on the silicon. The back conductors do not create any shade. So if I was able to place both of the conductors, the one on the top and the one on the bottom, then I'll get 100% of the area effective. So most of the sun's photons getting into the cell will face the 100% of the cell area.